Hey everyone, welcome back to the channel. Today I'm going to make a long form video that goes into a lot of detail around how I deal with supply chain challenges. It could be an electrical component that has a long lead time or is difficult to source for whatever reason. In today's case, it's a mechanical component that's used on this LED lighting product that you see on the screen here. This is actually an ultraviolet product. It's a UV blacklight that's used in themed environments and nightclubs and those types of applications. And what I want to do first is just open this thing up so we can get a better look at the component. So there's 6 screws total. You can see I'm going to remove 3 screws from this side and then I'll remove 3 screws from the other side. What you'll notice when I flip this over is I'm going to use this little pen magnet over here to the side to remove a trim piece. That's what keeps the screws hidden from the outside. Right there. Now when this last screw is removed, I'll be able to slide the electronics out of the die-cast aluminum enclosure. The first thing that you're going to notice is this black piece of glass on the front. This is actually a UV pass filter that's critical for the design. I'm going to go into a lot more detail into that filter later in the video. On top here, you'll see 9 optics. Those are actually the component in question. The manufacturer who makes those no longer makes them, so I now need to try to find a replacement. I'm now removing 5 screws around the perimeter of the LED board that hold it to the rest of the assembly. One neat design aspect of this fixture is that these screws actually thread down into brass standoffs that go all the way down to the driver components on the bottom. Those standoffs are actually used to carry the LED current from the driver back up to the LED board. So the simple act of removing these screws actually breaks the connection. There's no interconnects, no wire harnesses. It makes it really easy to change out these LED boards in the field. One final thing that you'll notice when I pull the LED board off is the copper heatsink on the back side. I'm going to go into a lot of detail in this video on that heatsink also. Okay, so here's a data sheet for the optic that I'm currently using that's now obsolete. And we can see it's OD, its outer diameter is 21.6 millimeters. So the first thing I'm going to do is look for a drop-in replacement, something that I can literally just swap out. The closest thing I've found so far is this optic here. And so we can see its outer diameter is 21.7. 21.6 to 21.7, so that's a close fit. There's also these square optics available. Now the thing we need to remember is that this is a UV product, and most optics are made for the visible spectrum, and if you try to use an optic that's made out of a plastic material that's good for the visible spectrum, it'll quickly turn yellow and deteriorate under UV light. So that massively reduces the number of available optics that I can look for. And these are the best 2 choices I've found so far. The problem with this square optic is it doesn't fit very well onto my existing circuit board. So you can see here's just a quick scale sketch. Here's the 9 optics I'm currently using and how they fit underneath that black UV pass filter. And if I use the square optics, and leave a little bit of space between them, they're going to overhang the filter, which isn't great. I don't love that. Again, this optic looks like a better fit as it's virtually the exact same size. However, the problem with this optic is that its opening for the LED, this square opening right here, is 4.2 millimeter square. And the LED that I'm currently using is 4.4 millimeters. So I'm not going to be able to fit this optic on top of this LED. But I'm having trouble finding an optic that'll work for this LED. So I think what I'm going to do is I'm going to run with this optic and I'm going to look for different LEDs that are compatible with this optic. So even though the optic is the problem component we're trying to deal with, it's going to force me to actually look at changing my LED. So again, here's the LED that I'm currently using. You can see it's 4.4 millimeter square, and it's got this kind of funky footprint with 2 anodes and 2 cathodes, and then a thermal slug in the middle. So I found 2 LEDs so far that have similar specs that look like they might be a good replacement that also fit with this 4.2 millimeter square opening on this optic. Okay, and you can see these are a standard 35-35 LED footprint, they call it, where it's 3.5 millimeter square. And if we look at its footprint and its DIMMs, this other LED has virtually identical footprint and dimensions. So I think what I'm going to do is get some samples of these 2 LEDs, get some samples of this optic. I'll need to change my circuit board footprint from this footprint to this standard 35-35 footprint and run some tests and see how it looks. Okay, so here we are in Altium Designer. You can see this is the circuit board that I've been building for the last few years. It has that sort of funky LED footprint. And so the change that I need to make is relatively straightforward. I just need to swap out this footprint for that 3535 LED footprint. And I've gone ahead and done that here. So you can see here's the new 3535 LED footprint. Another thing you can see here, these 5 plated through holes around the perimeter. As we discussed earlier, I use those to bring the LED current from the driver up to the LED board. And you can see those holes are connected to the cathodes of the LEDs, so they all share a common anode. The driver pulls the LEDs low to turn them on. I've gone ahead and made these Gerbers, so I'm going to buy some prototypes. What I like to do when I need to buy a short run of prototype circuit boards is use this company called Osh Park. They do a nice job on their website giving you photorealistic renders of what your board is going to look like and all the different layers. One thing to note with these guys is these quick-turn prototypes only come in 1-ounce copper. In production, I use heavier copper than that, but for prototyping, this should be okay. When I run thermals on this, if everything looks good with 1-ounce copper, I can be assured it'll look good with heavier copper in production. So I'm going to go ahead and get some of these boards ordered, get the LEDs ordered, get the optics ordered, and I'll bring you guys back when I'm ready to populate the boards. All right, I now have my LEDs, my PCBs, and optics. So the next step is going to be to populate the boards. What you're looking at here is a pneumatic solder paste setup. In production, the paste is applied using a stencil, where the stencil is put on top of the board and the paste is sort of squeegeed through the stencil onto the pads. You can buy prototype stencils, but I find that to be kind of messy and cumbersome when I just need to build a couple of boards. So I usually end up using this pneumatic dispenser that you see here. Now the amount of paste being dispensed can be fine-tuned by adjusting the pressure going to the dispenser, or you can change out the tip size. These syringes just use lure lock tips, so you can buy different gauge tips, and that'll also help you fine-tune the amount of paste being dispensed. I'm running the dispenser here with a foot pedal manually, so as long as I stand on the foot pedal, the paste comes out, so I'm just doing quick taps. But you can also set up the dispenser to run based on an amount of time with 100 millisecond increments. So if you have a board with a bunch of, say, 0603 components, you could set up the time to dispense just the right amount of paste for those pads, and you could go through and blast out all those pads pretty quickly. This is a leaded alloy with a no clean flux that I'm using here. I find the temperatures required for lead-free alloys to be kind of a pain to deal with when I build prototypes. In production, obviously, we use lead-free solder to make sure that we're RoHS compliant. So you get the idea here. I'm going to go through and paste all the pads for the 9 LEDs. Let's switch over to placing the LEDs down onto the wet paste now. So I've made a little pile of LEDs next to the microscope, and I'm going to start placing them down onto the wet paste with tweezers. To get the orientation right, you can see I'm looking at the gold bond wires underneath the dome, and I'm lining those up to the anode on the circuit board. Then once I drop it down, I kind of squish it into place by giving it a little tap on top of the dome. The placement is fairly forgiving. You'll see me kind of drop the parts down and then sometimes nudge them into place. Once these go into the oven and the solder melts, the surface tension of the liquid solder will sort of drag the part into place if you were off a little bit, assuming that your footprint is designed right. While building these, it's important to keep your hands off of the LEDs, especially if they're UV LEDs. It's real easy to contaminate the dome with the oils in your hands, and I've done that before by accident. And what happens is when you run the board and then look at it with a FLIR infrared camera, you can see all the LEDs that aren't contaminated are running at, say, 60 degrees C, but the contaminated dome will be as hot as 100 degrees C. And I think what's going on is the oils in your hands just absorb the UV energy coming out of the LED, and it ends up just getting super hot. So again, I'm careful not to touch the LEDs as I'm putting them down. All right, after I place all 9 of these LEDs, I'm going to run them through the oven, then I'll flip the board over and we can start working on the bottom side. The boards are out of the oven, so now I'm going to work on the heatsink side of the circuit board that we touched on earlier in the video. This is a heatsink design that my team patented a few years back, and the patent doesn't just cover keeping LEDs cool, it actually covers keeping any electrical component cool. It has a lot of advantages for this exact application. So typically LED fixtures are designed with a metal core circuit board for the LEDs, and then they use a gap pad or a thermal grease as the thermal interface material when they mount it to an aluminum extruded heatsink. Whereas with our design, we use copper tubes and we solder them directly to the back of the board. So the thermal vias that you see here They're used to pull the heat out of the LED and conduct it directly into the copper tube. And of course, we're using solder as our thermal interface material, which is a better conductor than a gap pad or a thermal grease. We also don't need to use a metal core circuit board. As you can see, this is just a regular FR4 circuit board, so there's a pretty big cost advantage there. The copper pipes that we use are basically plumbing fittings. You'll see them in the next scene as I place them onto this wet paste. And with copper being such a good conductor of heat, you can really dissipate a lot of watts with each tube. So I'm just putting a lot of paste on these donut pads here in the video, but getting the right amount of paste for each tube in production is a little bit of a magic trick. Typically a 5mm thick stencil is used for most components, but we use a little bit of a thicker stencil when we do the tubes. So now you can see I'm placing the pipes by hand onto the wet paste. In production, our CM uses a jig to place these pipes. It sort of sits above the circuit board and it has holes where they can just drop the pipes into the holes and they perfectly align right onto the donut-shaped pads. Here I'm just being careful to place them the best that I can. Another thing you'll notice are the holes lined up with each tube here. This is an actively cooled product. There's a fan that sits right behind this heatsink. The idea when we designed this product was to make the highest power, most compact fixture that we could. These holes allow us to use a super slow fan that just moves a little bit of air and is really quiet. It turns out all you need to do is basically break the boundary layer of stagnant air that's sitting inside the tubes, and you can dissipate a ton of power. This design's also nice when it comes to replacing the LED boards in the field. They literally just unscrew the LED board, swap in the new one, and the heatsink comes fully integrated onto the LED board. Here you can see the oven that I use to reflow the solder. This is a modified toaster oven, basically. Those purple things you see on the top, those are fans hooked to some squirrel cage blowers that move a massive amount of air around inside the cabinet. And then over here on the right, this is a controller where you can program different profiles and it runs the heating elements to follow the profile. Running a little bit of a time lapse here, takes about 5 minutes total. When I filmed this clip, I had the toaster oven hooked to an outlet that I don't normally use, and turned out I think there was kind of a lot of voltage drop because the oven didn't have the balls it normally has to follow the profile. So you can see here I'm pressing the heat override button to make sure that I reach the appropriate temperature for the solder to flow. You might think that you'd need an extra hot profile to flow the solder with the pipes, being that they have such a high thermal mass, but it turns out that because they're a really effective heatsink at dissipating heat, they're also really effective at pulling heat out of the air. And so turns out that you can use essentially the same profile that we use on the component side to reflow the pipes. Once the oven reaches its peak, in order to follow the profile down, you need to crack the door. So I manually just open the door slowly as I watch the profile to follow it all the way down. Now with the boards built, we can start applying the optics. You'll see they come with double stick adhesive already applied to the back of them. I'm wearing gloves. Like we said, I don't want to contaminate the optic or LEDs here. If you look over on the left, you'll see my existing LED board in that strip of paper. Those are actually VHB double stick tape stickers that we laser cut. We have to custom make because the existing optic didn't come with adhesive already on the back. So this is actually a pretty big improvement to the manufacturability in that the new optics already have the adhesive on them. When you're applying these, you can feel that square cutout slip over the LED, so you can be assured the optic is dead centered before you stick it down. Now before I apply the final optic, I need to install a thermocouple on one of these LEDs so I can do thermal testing to make sure I'm not running them out of spec. So here we are back under the microscope. You can see the first thing I do is I come in right on top of these thermal vias and I use an X-Acto to scrape away the solder mask. This is where I'm going to apply the thermocouple. The manufacturer of these LEDs instructs you how to do thermal testing, and they essentially say to get your thermocouple as close to the slug as you can, right here on the top side of the circuit board. So once the solder mask is scraped away, I come in with the biggest tip to my Metcal iron to get some solder to flow onto the spot that I scraped away. You need a lot of heat here because, again, there's the copper tube heatsink right underneath those thermal vias. So if you don't come in with a big tip, you'll never be able to get the solder to properly flow. Then I come in with a J-type thermocouple that I've made, and I try to get it as close as I can to the LED. Then I give it a little pull test to make sure that it's on there well. Now I'll install the last optic and bring the fixture over to the environmental chamber. I'll load the fixture in and run the thermocouple out the hole in the top. The fixture has an automatic thermal shutdown, so I'm going to bring it right up to its maximum ambient of 45°C and make sure it shuts down, all the while logging the temperature of the LED. And again, I have two LEDs that I'm testing here, so I'm going to be doing this test twice to make sure both of the LEDs are running within spec. Okay, so here's the data from one of the LEDs from inside the environmental chamber. And there's two things that we're going to look at here. We're going to make sure we're not running the LED hotter than what the datasheet says, and then we're going to look at how these temperatures affect the LED predicted lifetime. So what you're looking at is the top graph is the ambient temperature from inside the chamber, and the bottom graph is the LED case temperature from where we put the thermocouple. They allow 100°C maximum junction temperature for this LED, and we're not measuring the junction, we're measuring the case, so we need to calculate the junction based on the thermal coefficient of 1.4°C per watt. We're running the LED at 3.7 watts, so what we do is we multiply our 3.7 watts times 1.4°C per watt and add that to our maximum measured temperature. That gives us an 80°C calculated junction temperature, which is under 100°C. So we're good as far as the maximum junction temperature goes for this first LED. Now, this chart over here is the lumen maintenance, or in this case, it's sort of power maintenance, since there's not really any visible lumens coming out of a UV LED. And these charts typically aren't on the datasheet. You usually need to contact the manufacturer directly to get these charts. In this case, they provided me the chart at 1 amp, which is my drive current, and they gave me two lines. One of the lines is predicted lifetime at a junction temperature of 60°C, and one of them is predicted lifetime at a junction temperature of 80°C. And so if we look at the lifetimes here, we can see that we have 15,000 hours of life before the LED has dimmed down to 50% when it's running at room temperature. And we have 10,000 hours of lifetime before the LED has dimmed down to 50% when it's running at its maximum ambient. And that's not great. I don't love that. So let's take a look at how the other LED compares. Here's the temperature data from the second LED. And they only allow us a 90°C maximum junction temperature. So if we look at where the fixture is rated, an ambient temp of 45°C, we measured a LED case at 73°C, and again, if we calculate what the maximum junction is, we can see we're right at 90°C. So we're okay in terms of the maximum junction temperature when running the fixture at the maximum allowable ambient. Now, as far as the lifetime goes, these numbers look a lot better. First of all, on the previous LED, the data that they gave us was down to 50% brightness. This data is only down 30%, right? So we're still at 70% of our original brightness with this data. And as we can see, at the low ambient temperature, if we run these numbers here and we follow this chart, we can see that we're at 35,000 hours and we're only down 30%. We're still at 70% brightness. The other one was 15,000 hours and it was down at 50% brightness. So this is more than double the hours, and we're only down 30% instead of being down 50%. So based on that alone, this LED here, my second LED, is the clear winner, and I'm going to run with that because its lifetimes are just so much better than the first LED. And while I'm on the topic of temperature data, I should point out that I don't only take temperature data on LEDs. You can see here, I take temperature data on all the critical components within a product like this. So here's a chart that shows ambient temperature. You can see I thermocoupled a switcher, I thermocoupled some FETs, sense resistors, a transformer, LED. Taking temperature data like this and making sure none of the components exceed the manufacturer's recommendations is one of the most important things you can do to maintain a reliable electronic assembly. Now that we have the LED selected, let's go ahead and take some optical measurements. I want to spend a couple of minutes talking about the UV pass filter that we saw earlier in the video. You see it here on the screen. So this isn't really part of the supply chain problem that we were having with the Optic, but while I'm making all these changes to the fixture, I want to take this opportunity to look at an alternate supplier for this filter. The supplier I've been using has been slowly increasing their prices over time, and it's at the point now where this filter is just really expensive. So the reason why this filter is required in the first place, if we look at the spectral output that's on the datasheet for the LEDs, you can see that they show that the peak is going to be right around 365 nanometers, and it tapers off quickly to the point where there's no visible light. From 400 to 500, this is going to be in the visible spectrum, and you can see that they show virtually no visible light coming out of the LED. However, this isn't exactly true. This graph probably is accurate for the die all by itself, but as soon as the LED manufacturer packages the die and puts a glass dome or a silicone dome on top of it, there's going to be some impurities in those domes that fluoresce under the UV energy and actually let out a little bit of white light that's visible. And so again, this graph is probably accurate for the die, but it's not accurate for the packaged LED itself. And that visible light is a little bit of a problem on stage performances that are using blacklights. You really want all of the light coming out of the fixture to be completely invisible. So the way that you deal with that is you actually get a filter that passes the UV part of the spectrum, but completely squashes the visible part of the spectrum. This way, coming out of the fixture, all you have is ultraviolet light. You don't have any visible white light coming out of the fixture. Now, the existing filter that we use is molded. You can see it here. This is actually poured liquid glass into a mold where we then insert magnets into the corners to be able to stick it onto the front of the fixture. With the supplier that I'm looking at as an alternate, we're not going to actually have them mold the sample. They're just going to give me this round sample here. So what I'm going to do is I'm going to set up the fixture, I'm going to set up a spectrometer, and I'm going to look at how the existing filter that I've been using compares to this new sample that I got. Okay, so what you're looking at here is the fixture set up with no filter in front of it, and the spectrometer is pointed at it a couple meters away. And so this is the visible part of the spectrum here. So this is that unwanted sort of white light that I was talking about. The ultraviolet part of the spectrum is off the screen to the left. There's quite a bit of noise on this measurement just due to the dynamic range of the spectrometer. It's seeing this giant peak off to the left, and relative to that, this white light is kind of dim. So as I play this, I'm going to come in with the sample filter and drop it in, and as I get out of the way, you can see that the filter does a really nice job squashing all of this visible light. And this isn't a real scientific measurement here. I'm just trying to kind of compare this new filter to the old filter in sort of just a relative way. So then I'm going to pull out that new filter and I'm going to drop in the old filter, and we'll see how it looks. And you can see it looks exactly the same. Right, so in terms of the new filter squashing that unwanted visible white light, does a really good job. Now let's take a look at how it attenuates the peak at 365 nanometers. So now I'm dropping in the new filter. And the units aren't real important here, but we're going to look at the absolute irradiance, and we can see that the peak of this is at 72. Now I'm going to pull this filter out, and we'll drop in the existing filter. You can see I drop it in there with the magnets. And it's also measuring 72. So we can see that the new filter attenuates the 365 peak exactly the same as the old filter. So I can confidently say that that new filter will work the same as the old filter. So now let's take some measurements to see how the new optics, the new LEDs, and this new filter compare to the old optics, the old LEDs, and the old filter. What we're looking at here are a couple of simple photometric plots that I just took. So what we end up doing is we set up the spectrometer at different distances to measure the brightest part, the center of the beam. And I use a handheld meter to make sure that my spectrometer is calibrated. So you can see we measured the brightness at 1 meter, 2 meters, and 3 meters. This is the new LEDs, the new optic, and the new filter. And this is the old LEDs, the old optic, and the old filter. So that lets us know the brightness of the center of the beam. Then in order to sort of quantify the shape of the beam angle, what you do is you slowly rotate the fixture so it's no longer pointed directly at the spectrometer, and you keep rotating it until you're at half the brightness that you were at the center of the beam. And that's essentially what they call the beam angle. So you can see my beam angles at the 50% intensity spot are the same between the new version and the old version. And then what you do is you keep rotating it further until you're only at 10% of the brightness as you were at the center, and that's what they call the field angle. And so again, you can see the field angle and the beam angle are the same. So these beam shapes are the same. Now, if we look at the brightnesses at different distances, you can see the new version is twice as bright as the old version. So at 1 meter, we're at 4.1 milliwatts per centimeter squared. And with the old version at 1 meter, we were at less than 2. So I'm more than twice as bright. And I sort of knew that that was going to be the case by looking at the data sheets of the LEDs, but I am pleasantly surprised to see that it's literally twice as bright. So now let's look at the wide version. So with our old fixture, we had two SKUs. We had a narrow version and a wide version, but the optic was only available in a narrow beam angle. So the way that we achieved a wide spread was by texturing the black filter. We actually sandblasted the back of it, and that's a pretty inefficient way to spread a beam. However, our new optic is available in a natively wide beam angle. So you can see here, I'm comparing the new LEDs with the wide optic and the sample filter. to the old LEDs with the narrow optic and the sandblasted filter. And it turns out that that actually gives us another multiplier in terms of brightness, because sandblasting the glass is so inefficient. If you look at the brightness here, you can see that at 1 meter, I'm at essentially 1 milliwatt per centimeter squared, whereas with our old version, I was at 1/3 of a milliwatt per centimeter squared. So now I'm 3 times brighter by using the natively wide optic. If we look at the beams, you can even see that my new version is slightly wider than the old version. So not only am I 3 times brighter, but I'm covering even a larger area. So I think what this means is I'm not even going to need 2 SKUs of this new version. This wide optic is going to retain the punch of the old narrow version while covering an even wider area as compared to my old wide version. So let's go ahead and do some real world tests now and see if that's true. Okay, so what we're looking at here is a giant tapestry that I have set up as our final test to compare the new version to the old version. It's 8 feet across by 8 feet across, and the fixture is about 8 feet away. And what we're looking at here is the old wide version, right? So this starts off with a narrow optic, and then it goes through the sandblasted old filter. For all these tests, I left the camera settings the same, so they should be pretty realistic in this video to how they actually looked in real life. So you can see it's hitting the whole tapestry, but there's not a whole lot of punch here, okay? So this next clip is the old narrow version. So again, you can see we're really hitting the middle well, but over here on the sides, there's not a lot of punch. You can see I'm slowly twisting the fixture back and forth so you can kind of get an idea of the beam size. So again, this is the old narrow version with the old lens, the old narrow optic, and the old LEDs. This next clip is the new version. So as you can see, it's completely hitting the whole tapestry, and it's also maintaining the punch of the old narrow version. So this is the wide optics, the new wide optics with the new LEDs and the new filter. You can see it just does a really good job hitting the whole tapestry. Here's sort of a comparison of all 3 of them on top of each other. Okay, so you can see this top clip. This is the old wide version, really lacking punch. This one in the middle, this is the new version, and this one in the bottom is the old narrow version. So again, comparing these two together, you can see that the old narrow version really doesn't have very much punch off to the sides. It's really only bright in the middle, and that's because it was a narrow optic. Whereas our new wide version maintains the same punch that the old narrow version had, but it hits the whole tapestry. So again, I think the prediction is correct. I don't think we're going to need 2 SKUs with these new brighter LEDs. I think we're going to be able to just have a wide version that maintains the punch of the old narrow, yet covers as big of an area as the old wide did. Here's sort of an A/B comparison of the old narrow versus the new wide. And again, if we look right in the middle, we totally maintain the punch that the old narrow had, but we cover all this area on the outside with the new wide optics, the new LEDs, and the new filter. I think at this point we can call this project complete, so now I just need to package up all the files, send them off to my CM so we can begin building this new version. If you enjoyed this video, go ahead and subscribe to my channel. I plan on releasing more content similar to this in the future. Thanks again for watching.